So we now have Antonia Paraskevopoulou to tell us a little bit about the domain wall bound on AdS flux vacua. Take it away.
Thanks for the introduction. Thanks to Lorenzo for a very nice beginning of the session. And of course, let me thank Bruno and Filippo for the invitation. I'm very happy to be presenting my work here again. Today, I'm going to be talking about the domain wall bound on AdS flux vacua. This is based on a paper that appeared recently with Niccolò Cribiori and Thomas van Riet, both at Leuven. And and the main underlying principle behind this talk is actually IR UV mixing. This is a property that appears in various forms in quantum gravity, is also in holography. And in fact, what I'm going to be talking about today is very closely related to an inequality you might already be familiar with, going under the name of the covariant entropy bound. So to give you a brief outline of the talk, I'm going to start by translating this bound into EFT terms in the context of anti-de Sitter space, just to compare with other applications. But then I'm actually going to switch gears and try to see whether it's possible to derive such a bound from supergravity principles using domain walls. We're then going to proceed with checking some examples which respect or violate this bound. And in the end, I'm also going to try to give an intuitive picture of what it means for this bound to be violated. So first things first, why was I saying that this bound is a manifestation of UV-IR mixing? Now, typically this bound is formulated on light sheets, more complicated surfaces, but if we consider an AdS space, which is what I will be working on in this talk, the picture simplifies significantly. We can think of an EFT of n particles. This is going to be in a region of AdS space, which will roughly have a radius analogous to the inverse of the minimum energy that this EFT sees, its IR cutoff. And its entropy is going to be related to the number of particles that populate it and the volume it spans. Plugging this information into the covariant entropy bound, you can directly see how it mixes UV and IR scales. We actually obtain an upper bound for the UV cutoff in terms of the IR cutoff. But of course, the question is, what can we actually plug into such an expression? One might say that what would be an appropriate UV scale is in a sense more obvious. We have obvious candidates. If we're coming from compactifications, one would be the Kaluza-Klein scale. If we think of quantum gravity applications, we can think of the species scale. But it's actually less trivial to deduce what would be the best IR cutoff to place here. Now, in AdS, this picture simplifies because we have an obvious candidate, which is the inverse of the AdS scale. One can wonder if this is really strictly the IR cutoff of the theory, because we might consider, for example, larger lengths. But the nice aspect of this inequality is that if you're overestimating the IR cutoff or underestimating the UV cutoff, then the actual theory would still satisfy it. But the question I want to answer first is, could we find such a bound naturally in the context of string theory compactifications? And in fact, this is what we did. We performed a quite standard exercise, starting from the 10D equations of motion and combining them with the dilaton equation, assuming a constant dilaton factor. We can actually get rid of the H fluxes and relate the Ricci scalar to R fluxes and contributions of extended objects. Now, again, because we want to work in a d-dimensional AdS space, we would like this factor to be negative, which will be the case if we only have d branes, or if we have all planes which are combined in such a way such that they are not dominated. This, for example, will be the case if one assumes what is called a detailed balance condition, so that the various terms are roughly of the same order. If we are in such setups, then indeed we can lower bound the inverse of the AdS radius by flux terms. Still, we're not quite there to make such a bound evident. We would need to also make the UV scale appear in this expression. And in fact, this is also possible, taking into consideration the quantization condition for the fluxes. We see that the previous right-hand side actually transforms into a domain wall formed by wrapping an 8-n brane around the p cycle and smearing over the remaining ones. For simple compactification spaces, we have an additional factor larger than 1, so that basically we can lower bound the inverse of the AdS length with the tension of a domain wall. If we further assume that such a BPS domain wall is fundamental, we cannot actually probe it within the EFT, then this domain wall, its tension should be above the UV cutoff of our theory. And imposing this, we obtain a bound very similar to the covariant entropy bound, but observe that here we avoid various subtleties that one would have to deal with when dealing with the covariant entropy bound, as both the AdS scale and the UV scale naturally appear just from the equations of motion. And in fact, these arguments were first outlined in the context of 2D AdS vacua, where they forbid scale separation. But in the rest of this talk, I'm going to be considering D larger than 2. And in fact, I'm mostly going to be talking about 4D vacua. Another interesting aspect of this simple proof is that it can also be understood as a derivation of the Gravitino conjecture by relating the Gravitino mass to the AdS scale. And of course, the natural next step is to consider what type of models would satisfy this bound or not. Actually, it turns out that very famous models satisfy this bound, such as the class of DGKT vacua. Now, these are compactifications of massive type 2A on a Calabi-Yau, which have the nice property that basically all of the interesting quantities depend only on one parameter, the 4-flux quantum. One can consider what are the possible domain wall tensions in this setup, the lightest one being the one constructed by D4 branes, which, if this is a fundamental domain wall, should have a tension lying above the cutoff. And indeed, this is the case. This is a weakly coupled decompactification limit if we consider n to be very large. And indeed, the bound is parametrically satisfied. In the context of the covariant entropy bound, this was already checked in the literature, but in our paper, we also went beyond the original DGKT model into checking also anisotropic variations of it, as well as the equivalent models coming from compactifications of massless type 2A. Again, the picture is similar. If we consider the relevant domain walls also for that setup, we will see that assuming that the UV scale is given by the species scale, the bound is satisfied both at weak coupling, where the cutoff is going to be given by the string scale, and at large coupling, where the cutoff would be the higher dimensional Planck scale. And in fact, the same also holds for the 3-dimensional version of DGKT with similar arguments. DGKT fulfills the details balance condition, so in a sense, it is expected that this satisfies our bound. But in fact, we can already go beyond the previous proof. For example, we can consider the large volume scenario. This is a non-supersymmetric AdS vacuum coming from a compactification of type 2B on a Calabi-Yau. And again, one can actually even faster check that our bound is satisfied by observing that it satisfies the AdS distance conjecture, so that the naive cutoff of the 10-dimensional Planck scale would saturate the bound, but actually the real cutoff, we are again at weak coupling, the string scale, satisfies this as an inequality. And here I'm ignoring multiplicative factors appearing in these relations. So far, so good. It is interesting that AdS models without known CFT duals actually satisfy a bound which is very closely related to holographic bounds. But of course, the more intriguing question would be, what would be a setup where our bound could be challenged? Just looking at the form of this bound, one can already suspect that such a setup should possibly have a very large AdS length, but still not having managed to lower the UV cutoff in an appropriate manner. So in fact, we are curious about such possibly extreme hierarchies. And in fact, a mechanism that typically allows one to achieve such hierarchies is the racetrack mechanism, KKLT being one of the most celebrated examples of using this mechanism. Now, just to briefly remind you, in KKLT, what we try to do is construct the sitter minima by uplifting a supersymmetric 4D AdS vacuum coming from compactifications of type 2B on a Calabi-Yau, where one typically also adds some object, a wrapped anti-D3 brane, to go from an AdS to a de Sitter vacuum. Here, I'm actually not only going to focus on the AdS part of KKLT. I'm not going to comment at all on issues related to the control of the uplift. Of course, there's also work on this, but focusing on the AdS part, we might think that this setup actually is not compatible with our proof, because the classical flux contributions here all sum up to zero. Perturbatively, we have a flat vacuum, and it is non-perturbative terms that actually set the AdS scale. However, if one considers this more carefully, and we look at the superpotential governing KKLT, one realizes that we're actually very close to the final step of the previous proof. And what I mean by this is the following. Already for the classical part of the superpotential, the Gromov-Vafa-Witten superpotential, we know that this can be typically related to domain walls constructed from 5 branes. And in fact, it turns out that the situation is also similar even when we have such a racetrack-like superpotential as at the supersymmetric minimum. We can check that again, the AdS vacuum energy is related to the tension of a domain wall. Now, if we assume that such a BPS domain wall is there, and again, that it is fundamental so that its tension should lie above the cutoff, we are basically back to the last step of the previous arguments, that this should be above the cutoff of the theory. This is related to the AdS scale or the IR cutoff, and we would be performing a similar check as before. For what follows, as a UV cutoff, I'm going to be considering the Kaluza-Klein scale. One might think that this is possibly an underestimate, but by the structure of our bound, an underestimate should even more comfortably satisfy our bound. And the reason for this is that although we'll be initially considering AdS solutions without warped throats, if one also adds warped throats, it is more complicated to properly determine the UV cutoff, although there have been suggestions in the literature using also swampland arguments. But starting from the simplest setup, it has been suggested that one can construct KKLT-like AdS vacua without including warped throats and achieving exponentially small cosmological constants. And it turns out that if we go through the examples of this paper, not only is our bound not safe, but actually we observe extreme violations of several orders of magnitude. Too many to think that maybe this could be justified by some missing order 1 factor or anything. We get very large numbers. This is already very interesting, but one might think, okay, is there any chance that the situation changes if I add a warped throat? Now, first of all, this is a very non-trivial assumption because so far, typically, as far as I'm aware, there is no argument for why a warped throat would be needed for the consistency of the AdS vacuum itself. Typically, the motivation to consider warped throats is for the later uplift. But even if we put this comment aside, although we checked the so far best understood constructions suitable for KKLT de Sitter vacua, it is not clear that they are completely safe. Although we do not find such violations, it is not very clear that the bound is respected in a way that would indicate that the models are safer than in these extreme setups. And this is, in fact, not a very surprising result. There have also been other works arguing that perhaps the AdS part of KKLT is already problematic. Again, I'm ignoring at the moment also any arguments related to problems related to the uplift. And in fact, very similar arguments have been drawn also for the final de Sitter phase using the covariant entropy bound. So one might say, okay, we have found a situation where the bound is violated, even in an extreme manner. What is actually happening? What is going wrong? Is this a small problem or actually a very serious issue? Now remember that in all cases, our final argument for actually starting to considering the cutoff of our theory is demanding that if we have a BPS domain wall, this should be fundamental. It should not be something that we can probe within the energy scales accessible to the EFT. So it would be natural to consider that the violation of the bound means that this is no longer the case. We cannot consider the thin wall, the domain wall, as being thin. Now, I'm going to focus in the 4D setup with minimal supersymmetry, type 2B and Calabi-Yau, because this is also the only case where we found violations. And one can very easily realize that just looking at the tadpole condition, if we're trying to change the H flux, assuming we are not changing the topology of our theory, this could imply that we're changing the effective number of D3 branes available. And in fact, we can try to extrapolate the lessons of the KPV setup. We can think that the microscopic realization of our domain wall is actually an NS5 brane wrapping a 3-cycle dual to the H flux that is changing. In order to make sure we have no problem with anomalies, this implies that inside this domain wall, we have M plus N D3 branes. M is the flux piercing the cycle. And then, in order to obtain an even more microscopic picture, one can consider the following. These ND3 branes are able to polarize into a new NS5 brane. So we can understand this flux transition as this 2-cycle that is wrapped by this new NS5 brane moving. And in fact, one would in any case think that if this domain wall is actually part of our theory, if we have more elements in the theory than we initially thought, this should be equivalent to new degrees of freedom being part of our theory. And it turns out that this scalar, which describes the position of this 2-cycle, is exactly such an example of a degree of freedom. So one could ask themselves, okay, what if I try to integrate this in? If the resolution of the violation is that the domain wall is not fundamental, I should be trying to do this. It turns out, again, by extrapolating KPV-like results, that we can describe the potential for this axion-like scalar so that we obtain a periodic function with characteristic energy scale given by the same energy scale that we would associate to the domain wall if it was thick. The problem with this is the following. We are thinking that the violation of the bound means that this is an energy scale which is easily accessible in the theory. It is much lower than the UV cutoff. But this means that it is possible for us to provide energy to the system that would allow us to move from an initial vacuum to infinitely other equivalent vacua. And this is very counterintuitive to what one would typically expect for a standard QFT. So for us, the intuitive picture is that it is actually not so simple to bypass a violation of our bound, but it actually means that one potentially has problems with defining even the vacuum of this theory. So just to summarize, what I have tried to argue for today is that we can have a string theoretical realization of a bound, our domain wall bound, similar to the covariant entropy bound in the context of AdS flux vacua. The way I motivated this was by a simple supergravity setup, or by considering cases where the AdS cosmological constant is actually described by a domain wall, which we were assuming to be fundamental, and therefore its tension should be above the cutoff. And it turns out that both TGKT and LVS casually respect this inequality, whereas the same does not seem to be obviously the case for KKLT. Especially for the cases without warp throats, we actually found extreme violations. And then we actually have an intuitive picture for what it means for a theory to violate this picture. Not only does it mean that we have not correctly accounted for the degrees of freedom included in the theory, but that we should also reconsider the vacuum structure of this QFT. So overall, the message is that this bound is actually very non-trivial if we are interested in constructing AdS vacua with very small cosmological constants. And of course, this is something we would really like to do in the context of string theory, because if we would like to match today's observed dark energy density, which is extremely tiny, one way to do this would be to construct an AdS vacuum with a very small cosmological constant and then trying to uplift it. And apart from this lesson that there should be more constraints that we can impose in order to perform our model building, there are many ways to extend the current analysis. An obvious one being that we would like to better understand possible violations by improving our approximations for understanding these domain walls. It would also be very interesting to try to more directly relate our domain wall bound to holographic or entropy arguments. Although on one hand, it was very straightforward for us to have domain walls, it would be very interesting if we could connect this to a discussion that has been actually very active recently about whether such models like KKLT can admit a holographic dual and what would be the properties of that, and so on and so forth. And additionally, one could wonder if we can obtain even more constraints for such AdS vacua and about the H-shaped hierarchies. But this seems not to be so easy. For example, one could consider the CKN bound. It has a very similar structure to the covariant entropy bound or our domain wall bound. It again relates the UV cutoff to the AdS scale, or if you would like, the IR scale. But as it stands, we're not able to provide such a microscopic realization for it. So with this, I'm going to stop here. Thanks a lot for your attention. I'll be happy to answer your questions.
Thank you, Antonia. Are there questions for Antonia?
Can I ask a question?
Yeah, go ahead.
Okay. Just do you think it's a strong assumption to say that, like, in the KKLT domain walls, the tension is like purely set by the flux potential?
Sorry, I didn't hear the beginning of the question.
Yeah. Do you think it's a strong assumption that for the KKLT domain walls that like this tension would be like set purely by the flux superpotential?
I mean,
Yeah, because you say something like typically, so I was just like.
So the fact that the same relation that holds for the classical part also holds for the entire solution, I think this is easy to see by applying the supersymmetry conditions. I think what is perhaps not so trivial is whether indeed the geometry allows for the construction of such PPS domain walls. Now, first of all, I think it's actually quite difficult to prove that this is impossible. Apart from this, one can even consider that instead of having the appropriate geometry, you can consider a more general calibration than assuming you have a special Lagrangian cycle. And still, even if that was, even if all of this fails, I mean, first of all, you can say that, okay, if we really do not have a BPS domain wall, then simply our proof does not go through. So one would need additional arguments. But one could also consider the cases of warped throats, where I think, at least for the examples we checked, it is assumed that at least there is such a cycle in the throat. So you could play the same argument, but this time considering dualizing the fluxes which live in the throat and not in the bulk. But then again, I should stress that such clear violations were only able to obtain in the context of having no warped throats. The warped throat analysis was not so conclusive.
Okay, thank you.
Thanks.
Since you just mentioned the warped cases, can I ask you something about that as well? If you go back to the previous slide, when you say that considering the Kaluza-Klein scale might be an underestimate, what do you mean exactly? That you're looking at the bulk KK scale versus warp KK scale or something like that?
First of all, even if we have no throat, you could say that, for example, this is a decompactification limit. I can consider the Kaluza-Klein scale or the string scale as the cutoff. In the context of a warped throat, I would actually be considering the warped Kaluza-Klein scale, which is in a sense the energy scale of the lightest tower. I would expect that the cutoff is at least the quantum gravity cutoff is a bit higher than that. But again, so the idea for us is that if we consider the lowest candidate, then this should have been the easier case. If the bound is violated already for the lowest possible candidate, even if you have a better proposal, as long as it's higher than that, it would face even more serious problems.
Mm-hmm. But in this case, even in this decompactification limits, you're using the Kaluza-Klein scale instead of the higher dimensional Planck scale, like what you would call the species scale in those cases.
Yes, or the string scale.
Or the string scale. Okay. Are there other questions? Okay, I don't see any other questions. So if not, we can thank both speakers again. And if you have more questions, I think you can stay around for a bit and ask any of them. Otherwise, see you next week. Well, in 2 weeks, sorry.